All right, everybody, it is 6 p.m. Central Time, so we're going to go ahead and get started with our chemistry webinar tonight. We haven't had a chemistry webinar for a little while here at Archer Review, so I'm so glad you guys signed up and you are here with us this evening. So just so everyone knows, my name is Amber Whitney. I'm a science educator here at Archer Review, also a science educator by day, by the way, in public schools. And I'm just happy you guys are here tonight so we can talk about all things chemistry related. But while we wait for a few more people to hop on, let's go ahead and talk about some other details and really awesome things we have going on here at Archer Review. So this slide has various QR codes for you to access all of what we are able to supply you with as a pre-nursing student here at Archer Review. A really awesome feature that has rolled out recently are the on-demand videos. So these webinars, if you've attended them in the past, you know that they're kind of fast-paced, a little surface level. It's a crash course, so to speak. Definitely not all the details you may want or need for that TEAS test. And so the on-demand videos allows you to really tailor your needs to different skills that you need to improve on to really prepare yourself for that test. And the on-demand videos allow you to have that access. So as we go through the chemistry learning tonight and you feel there's a topic that you would like to go into greater detail on, or go into it as a slower pace or need some different practice questions, check out those on-demand videos we have on our website. You can use the QR code that's there for quick and easy access. And the extra great thing about our on-demand videos, we have timestamps on them. So let's say there's a topic that you want to improve your learning on, but maybe you just want the practice problems from that topic. There's different timestamps built into each video where you can quickly jump to that appropriate spot without having to watch that entire section over. So really awesome things we've got going on at Archer. Don't forget about the free question bank as well. So there's a QR code here for that. We've got over 1,500 questions for you all to study and help you prepare for your TEAS test. So check out that free question bank. I'll give you some questions tonight to engage in. But again, if you need more, you just need different styles, that free question bank is there for you. And if you've missed any webinars along the way, maybe you had intentions, but something came up, or you didn't even know that we offered a webinar, you can go ahead and check out this QR code where the rewatch option is, and you can access our playlist with all previous webinars, whether it be science related, reading, writing, or math. We've got you covered. So a lot of great resources for you all here as you prepare for your TEAS test. And before we officially start, I'm going to give you this QR code ahead of time. This QR code will send you to a feedback survey. I just want you to scan that now so that it's up and it's ready and you don't forget about it by the time you check out of this webinar. So I take the feedback very seriously as an educator. I am here to help you in any way that you need that I can provide. So please take time to fill out that survey. All of us here at Archer Review really cherish that feedback that you guys give us. Trust me, we really look into it all so we can help you in the best ways that we can. So please take a moment to fill out that survey whenever you wrap up this webinar. And with that being said, let's go ahead and begin with our first section. So I just want to kind of engage your brain for a minute about the topic chemistry, because I'm a life science teacher, really. My passion is biology and anatomy, but I love chemistry too, because as a pre-nursing student, I'm sure you share that similar passion with me. You love the human body, the structure, the function. But to really understand what's going on inside of a living being, to really be able to explain the science behind why, brings you down to that molecular level, which is the chemistry level. And so understanding chemistry is really essential to your overall understanding for how life exists and how life functions. So we're going to start with the atomic structure, chemistry 3.1, this section of our science. And with the atomic structure, we're talking about just like the basic atomic level. So let's begin. So let's begin with what are atoms? So atoms are the smallest building block of all matter. All matter, living or non-living, everything is made up of matter. So the smallest building block of any form of matter are called atoms. And we know it's the smallest building block because it cannot be broken down any further and still hold those same properties. So atoms can take on various forms. You can have atoms that make up a solid, atoms that make up a liquid, or atoms that make up a gas. So there are three forms of matter: solid, liquid, and gas. And when we break down atoms, atoms are arranged on a periodic table. So for us to continue breaking down the structure and function of atoms, we need to know how to review how scientists represent all the useful information about any type of atom. Specific atoms or specific types of atoms are called elements, and they are arranged on, like I said, a periodic table using element symbols in their own little square. So in each square, you will find a symbol, you will find the atomic number, and the atomic mass. All of these things together will help you understand the structure of an atom. So let's talk about what each one tells you. When we look at the symbol of an atom, so for example, here in our image, it's focused in on this symbol here, which is Si, which stands for silicone. So there's the name for the element symbol. Si is that symbol representing the atom for silicone. Oh, silicium, sorry, I'm referencing the wrong one here. So this shows the specific type of atom. Now, this element has the atomic number 14. And this atomic number is going to tell you really important information about this atom. It's going to tell you that there are 14 protons, and it will also tell you that there are 14 electrons if this atom is neutral. So atomic number will tell you number of protons. And then also on this element symbol will be another number. There'll be a larger number. This is the atomic mass. The atomic mass will include both the number of protons and the number of neutrons in that atom. So we've talked about protons and neutrons and electrons. Let's place where each one of those can be found in the overall structure of an atom. So any atom has this basic structure here. Inside the very middle, the nucleus of an atom, we can call it, you will find those neutrons and those protons. And then you see outside of this nucleus are various rings. You can call them orbitals. You could call them shells. Whichever way you call them, know that this is just an area that we recognize where electrons will be found. So electrons will be found outside of the nucleus of an atom, orbiting around, and inside the nucleus you will find neutrons and protons. So these subatomic particles, protons, neutrons, and electrons, have a charge to them. And these charges help you to understand the properties for how each type of atom would behave. So protons are positive. Think of like a play on the P sound. Protons are positive. Proton positive is a positive 1 charge. And its overall mass is 1 atomic mass unit. AMU is just a standard unit here for measurements. A proton, it has a positive charge of 1 with 1 atomic mass unit found inside the nucleus of an atom. Neutrons, as we spoke, are also in the nucleus of an atom with those protons, but neutrons are, think neutral. Neutrons are neutral. Neutral being that they don't have an overall charge. Their charge is 0. Neutrons are neutral, no charge. But they do have a mass, 1 atomic mass unit. And this is why protons and neutrons, having a mass here each, contribute to the atomic mass of the overall atom. And that final subatomic particle are electrons. Electrons are not found in the nucleus, remember, but looking at our visual here, they're found in those shells or rings or orbitals around the nucleus. And electrons have a charge of -1. And their mass is so minuscule, so small that we don't even recognize it as having a mass when we use the unit atomic mass unit. So it has an overall mass of 0, which is why electrons are not factored into the atomic mass that you would find on the element symbol on periodic tables. So a little bit more about each one. Protons are located in the nucleus, like I said, and protons determines the atom's identity. So if an atom has 2 protons, like we see in this helium atom here, 2 protons, then that atom has to be helium. If ever you come across an atom with 2 protons in that nucleus, it will always be helium. The number of protons determines the atom's identity. And don't forget, protons have a mass of 1 atomic unit, and so it helps to contribute to that atomic mass. Moving on to neutrons. Neutrons also are found inside of the nucleus, because they have they have 1 atomic mass unit for a mass measurement, so they will contribute to the overall atomic mass as well. When we think about neutrons, there's not one specific number on the element symbol on a periodic table that will tell you directly the number of neutrons. You are going to have to do some math to figure out how many neutrons are in each element or each atom of that element. And you can use the atomic mass and the atomic number to help you figure this out. So to find the number of neutrons, you would need to take the atomic mass and subtract out the atomic number, the number of protons. So let's practice on that helium atom here. We can see all components or all subatomic particles really easily. So in the helium atom, the atomic mass, you see 2 protons and 2 neutrons. Each proton has a measurement of 1. Each neutron has a measurement mass of 1. So we've got 4 total AMUs here, atomic mass units. So the atomic mass for helium is 4. And when you look at an element symbol for helium, the atomic number at the top would be 2, telling you that there are 2 protons. So you would take 4, the atomic mass, minus 2, the atomic number, and the number you are left with is 2. And so 2 is the number of neutrons you would find in that atom of helium. So you take the atomic mass minus the atomic number to find the number of neutrons. Now, some elements exist in alternative versions of themselves because those neutrons may vary in number. The protons do not change, okay, because the proton tells you the atom. The protons do not change, but sometimes your neutrons can vary in number, giving us what's called an isotope. So an isotope is an atom that have the same number of protons, but they have different numbers of neutrons. And isotopes are really helpful for many reasons in science, but especially for helping us date fossils to understand how old something is based on the decay. Isotopes help us diagnose and treat cancer through imaging. And isotopes help us understand heart conditions, or even can be used for bone scans. Isotopes are really helpful in the scientific or medical world. So let's break down how to interpret the information about isotopes. So we've got three different versions of oxygen here. Okay, that element symbol is O, stands for oxygen. That's consistent through all three visuals here. You also see the atomic number 8 is consistent in all three visuals here. Because remember, the atomic number refers to the number of protons. And the number of protons always remains the same if it's the same element. And these are all oxygen. So they all have an atomic number of 8. They have 8 protons in their nucleus. That never changes. But what you do see change down below is the atomic mass. And this atomic mass for this visual is 16. The atomic mass here is 17. The atomic mass here is 18. And remember the math I just told you about finding the number of neutrons. You take the atomic mass minus the atomic number, and whatever you get left over is how many neutrons there are. So for this first visual of oxygen, this first isotope, we take 16 minus 8, and we would end up with 8. So that means that there are 8 neutrons inside of this oxygen isotope. Okay, so how does that compare to the next one over then? Well, we've got the atomic mass of 17, subtract out 8 protons. How many neutrons then are remaining inside of that nucleus? So 17 minus 8 is 9. So there's 9 neutrons. This one had 8, but this one had 9. So see how they can vary in the number of neutrons, yet it's still an oxygen atom. That's an isotope. And that difference in neutrons in that atomic mass or in that nucleus alters the chemical properties and the behavior of that atom over time. And the decay, because of those properties, is something that we can harness in the scientific and medical world that's useful for us. So that wraps up isotopes. Let's go ahead and take a moment to just practice some basics on the element symbols. So for the carbon isotope, carbon-13, we can also call it C13, go ahead and take a moment to practice these 4 questions. What is the atomic number for this isotope? How many protons does carbon have based on this information? What is the atomic mass for this isotope? And how many neutrons are there? Feel free to share your answers in the chat. Just keep in mind on Zoom, I am able to see your responses, but no one else is. So that's definitely a safe place for you to share your ideas that I can quickly look over. On YouTube and Facebook, it's a little bit different. Everyone is able to see your responses there, but if you feel comfortable, go right ahead and share. And one more thing about questions for this webinar. There's about 50 questions, I believe, 50 questions on your TEAS test for science, and you have 1 hour to complete it. And only a handful of them are chemistry related. So I'm just going to give you about 1 minute per question. This one has 4 embedded in it, so I'll give you about 4 minutes to think through each one, and we'll come back and check and when your 4 minutes is up. All right, guys, hopefully that was enough time for you to tackle our first 4 practice questions. As I took a look in the chat, I see people are doing a really great job with just the basics so far. With that, I hope that's an awesome feeling for you all. So as we switch on over, let's talk about the answers to each one. So what is the atomic number for this carbon isotope? Remember, the atomic number is that smaller number found on that element symbol. So the atomic number here is 6. And that information tells us how many protons are present. So the first 2 answers here are both 6. 6 is the atomic number, and that means there are 6 protons. What is the atomic mass? That's that larger number found on that element symbol. And this atomic mass is 13. And so to find the number of neutrons, we take the atomic mass, subtract out that atomic number. So 13 minus 6 leaves us with 7. So there would be 7 neutrons found inside of this carbon isotope nucleus. So great job to everybody who shared their responses. Your responses look awesome. So let's keep going. Oh, I should mention, I've got someone in the chat asking about like sending an email through or sending this video through email. So here's just another friendly reminder that we have all of our webinars, not just this video, for free available on our playlist. So go ahead and move on over to Archer Review, or if you have these notes, take a look at that second page where there's a QR code and you can access all of our videos, not just tonight's video, but all videos that have been held previously. All right, electrons, that was one subatomic particle that I haven't broken down completely yet for you, but the electrons orbit the nucleus. Remember, they're found in those shells or those orbitals around the nucleus. And these shells can vary in number. So if an atom has that first inner shell, every single first shell will only be able to hold 2 electrons max, but every orbital outside of that inner shell or orbital, I use those words interchangeably, so I hope that doesn't confuse anybody, but I'll try to be consistent as possible. So this first shell here, see how there's only 2 electrons in that shell? But carbon actually has another shell outside of that first shell. And here is where we will be able to always find 8 electrons if they're available, if that atom can hold that many. So that first shell can hold 2 electrons, and any shell from the second shell onward can hold a maximum of 8 electrons. This is just really helpful information right now to front load with, so that we have that with us when we're ready to talk about electrons involved in chemical reactions later on. So electrons will also determine the chemical properties because of their ability to react with other elements in its surroundings. So the electrons will help you determine the chemical properties. It helps you understand chemical reactions, and they orbit that nucleus. But there's a specific type of electron that's involved in those chemical reactions, and they're called valence electrons. Valence electrons are found in the outermost shell. So looking at the helium atom, there's only 1 shell, so they would have 2 valence electrons, which just happen to be all 2 electrons that helium has. Carbon is different when you compare it to helium. Carbon's valence electrons are found in that outermost shell, so we're no longer looking at that inner shell anymore. Look at that outer shell for carbon, and carbon has 4 valence electrons in that outermost shell. Let's compare that to neon. Neon's outermost shell is completely at full capacity. Remember how we said that second shell and any shell after that can hold 8? Here we have a shell in neon that can hold 8 electrons. And this is that outermost shell for neon. So neon has 8 valence electrons. Now these atoms involved with like chemical reactions are either going to lose or gain these valence electrons, or they could share these valence electrons. No matter the situation, that's how chemical reactions take place, is through these valence electrons. These valence electrons are either being shared, they're being lost, or they're being gained. All right, moving on to ions. Still focusing on that electron subatomic particle. Ions are atoms that have an overall charge, and electrons have a negative charge, and protons have a positive charge. So ions are a type of atom that just have a different amount of protons compared to electrons, giving it an overall charge. So ions, if they are a positively charged ion, we call it a cation. This means that this atom has more protons than they do electrons. And remember, protons have a positive charge, electrons have a negative charge. So if we have more positive charges, the overall charge of that entire atom is positive. We call that a cation. And I'm kind of a crazy cat lady, and I'm sure some of you maybe can relate. So a little play on words here to help you remember. Think cation, like that, replacing that letter T for a plus sign to help you remember that cation is an overall positively charged atom. Or you can remember cats have paws, so you can replace positive for paws, like cats. Whatever situation works for you, I hope it clicks. Cations are positively charged atoms. So think hydrogen, potassium, sodium, and calcium. Anyone that have that little positive sign next to it, it's a positively charged ion. On the flip side, we have the term anion, and this is negatively charged ion. So this means that this ion has more electrons than they do protons, because electrons are overall negatively charged. And so if you have more negative attached to you, you're going to be an overall negative element. Okay, so anions are the negatively charged ion. And here are some examples. We've got fluorine, we've got chlorine, iodine, and sulfur, all with those negative charge next to it, because all of these examples would have more electrons than they do protons, leaving the overall charge for that atom as slightly negative. Let's take a moment to practice. Our practice question says, a chlorine atom has 17 protons, 17 neutrons, and 18 electrons, with an atomic mass of 34. What is chlorine's charge? And would it be considered a cation, an anion, or neutral, meaning it's not more positive, it's not more negative, it's balanced out? So what is the overall charge? And is it a cation, anion, or neutral? I'll give you 1 minute to work this problem out. All right, that was 1 minute. It sure goes by quick when we only do 1 minute type questions. So out of this question, the helpful information you need to know for overall charge is how many protons do you have compared to the number of electrons? The number of neutrons right now isn't really applicable, neither is the atomic mass. So when you compare number of protons, you've got 17 and you've got 18 electrons. So your overall charge, let me go ahead and click the next slide here, is going to be -1, because you have that one extra electron. And I see a lot of people in the chat chose that correct option. And you also identified that it's an anion because of its overall negative charge. Awesome work here. All right, let's go ahead and move on to the periodic table. So now that we know how to read each individual element and determine that critical information about its structure and some behaviors, let's see all of the elements together in the periodic table. Now, the periodic table, I'm sure you've looked at it, studied it in some sort of educational system before, but the periodic table, in case you've never really dove into it, is actually really highly organized and a really thought out table. So we've got three major groups that we're able to see here on the periodic table. We've got nonmetals, metalloids, and metals. So metals are numerous. See, that whole table is blue colored, lots of metals on the periodic table. And being a metal just means that it's malleable, it's conductive, it has some luster to it, it's ductile, like it can be drawn into wires. Nonmetals, the pink shaded here, means that it lacks the properties of metals. So it's the opposite of everything a metal is. It's a poor conductor of heat and electricity, for example, whereas metals are really great at that. And then metalloids, these few green shaded here on the periodic table, these are like metals, but not completely. They're in between metals and non-metals. So three major groupings here on that periodic table. But just wait, there's more. I told you it's highly organized, really helpful visual. So each of those three main categories, metals, nonmetals, and metalloids, can be broken down even further and organized into groups, which are the vertical columns, or periods, which are the horizontal rows. And these two ways to organize will tell you really helpful information that applies back to the overall properties of each atom and therefore its ability to react with others. So the groups, the up and down vertical columns, this will tell you how many valence electrons that this atom has. So for example, hydrogen is in group 1, so it's in column 1 with lithium, with sodium, and you can go down that whole entire column. This entire column here will all have one valence electron in its atom. So remember, valence electrons are the outermost electrons in the outermost shell. For hydrogen, there's going to be one. For lithium, there's going to be one. So that pattern is consistent all up and down that vertical column. But the rows, or periods, these will tell you the number of orbitals or shells that they have. So for hydrogen being in row 1, also in that same row as helium, there's only one shell around hydrogen, and there's only one shell around helium. And we saw that on our visual, our model for helium on a few slides back. There's only one shell around each one of those atoms. But when you go down to the second row, where there's lithium, beryllium, boron, carbon, you can move across. This entire second row will all have two shells around the nucleus of their atom. And then the third row will have three, and that pattern continues down the periodic table. So it's a highly organized, structured system that's able to reveal to you a lot of information that's helpful if you know how to interpret it. All right, let's review atomic structure basics. Atoms make up all matter. The subatomic particles that make up matter are protons, neutrons, and electrons. Remember that atomic number tells you how many protons are present in that atom, whereas the atomic mass tells you how many protons and neutrons are found in the nucleus of that atom. Isotopes are still the same atom, right? Like it never changes the number of protons. Oxygen was still oxygen, but they could differ in their atomic mass, which meant that they differed in their number of neutrons. Ions are a special type of atom that have a charge. Atoms can be positively charged or negatively charged. Valence electrons are electrons in that outermost shell and directly involved in the chemical properties of each atom. And the periodic table is highly organized by periods and groups and can reveal to us so much helpful information about each individual atom. Let's go ahead and move into physical properties and changes of matter. And I might have to pick up the pace just a little bit here because I see we spent about 30 minutes on just that first section. I can go on and on about chemistry, but I'm going to keep it within our time constraint because I know we all have busy lives and it's election night, and we're going to do our best to get through all of this really helpful learning by 8 o'clock as promised. And don't forget, if we go too fast, if you need to go into more depth, we've got those on-demand videos for you at Archer Review. Let's go ahead and begin with physical properties and changes of matter. So just a reminder, matter makes up all physical things in our universe and are composed of atoms. But the physical properties of matter differ. So matter has a mass, matter will have a volume, and matter has density. So let's talk about each type. Mass measures the amount of matter that makes up that object or substance. So it's just how many particles, how many atoms, what's the amount? Volume is the amount of space that object or substance takes up. And then density is the mass divided by the volume. So how tightly packed are all of these particles in a given amount of space? Or are they not as tightly packed and they're able to freely roam around? That concept applies directly into the states of matter. You can find matter in a solid, or as a liquid, or as a gas. So let's bring it back to the physical properties within each state. A solid type of matter means that those particles are tightly packed particles. They're hardly moving. Maybe they're vibrating in place because, everything has energy, but they're tightly packed together, giving that solid substance that you're able to touch, feel, see, and hold. It has a definite shape and it has a definite volume. But then we can also find a liquid. And a liquid has a little bit more energy going on into it. So those particles aren't as tightly packed and just vibrating in place. They have a little bit more energy, and so they're moving around more freely. So there's really no definite shape since they're able to move around in space, but there is a definite volume. And then finally, our gases. There are particles, but they are just buzzing around like crazy. When we think about particles moving freely like liquid, these particles move real freely. They move crazy all over the place. There's no definite shape and there is no definite volume here. But phases can change. And we see examples of this all the time. States of matter can be altered. See how there are arrows going every which way on this chart. So we're going to break down each arrow arrangement and identify what each phase change is called. And some of them you're going to know like the back of your hand. It's, it's common sense. Others we don't see as often in our everyday natural world. And so I just want to bring to light those terms as well. So this pattern shows how the phases of matter changes when heat is added or gained. So if we start here in the solid state of matter and we move through those arrows into the liquid and we move into the gas, it's moving in that direction because more energy is being added. And as we add more energy to each state of matter, see how those particles get shaken up a little bit more each time? So imagine I have a stove underneath of this solid. We turn the stove on, it starts to warm up. Imagine like an ice cube. An ice cube is sitting on top of that stove burner. We turn that burner on. Those particles begin to move around more freely because we're giving them energy through the form of heat. And as it gains that energy, these particles move and they move even more freely until that liquid turns into a gas. So phases can change from solid into liquid and into gas due to adding heat. So solid moving into a liquid is called melting. This is called melting. And then a liquid becoming a gas is called evaporation. So this liquid is gaining even more heat, and eventually these particles gain so much energy from that heat that they just escape the surface of that liquid. And that's what allows them to become a gas. So that's called evaporation. So solid to liquid's melting, liquid to gas is evaporation. But what about like the reverse order here? So we've got the same three states, but instead of adding heat, we're going to lose heat. So notice how these particles tighten up or condense over time. They're losing energy. They're not as wild and crazy. They're becoming more compact. So starting with the gas moving into liquid, this is called condensation. Gas becoming a liquid, condensation. And this is when heat is lost. So think of things that are cooling down in your environment, and then you might get like droplet particles on a surface. And then your liquid going into a solid, so liquid water going into a solid water form like an ice cube is called freezing. So those two, there's 4 phase changes, but those 2 slides I think are pretty much common sense for a lot of us. The freezing, evaporation, melting, condensation. It's the next 2 that we don't always see as frequently in our everyday lives. So when we start with a solid and we skip this liquid phase, we have a solid going directly to gas. Solid going to gas is called sublimation. And a classic example of this is dry ice, for example. When you buy dry ice and you let it sit, it just instantly becomes gas. It skips that liquid phase. That's called sublimation. But then, of course, that means gas can jump directly to a solid. This is called deposition. Think about frost forming on a cold surface from water vapor, for example. So gas going to a solid is deposition. All right, our first practice question with this next section. A nurse helps to remove a tumor from a patient's body and sends that tumor off to the lab. The lab analyzes the tumor and collects data on it in order to know how much space that tumor occupied in the patient's body. What property of matter is being analyzed here? Is it mass? Is it volume, density, or length? I'll give you 1 minute to work this problem out. All right, how much space that tumor occupies in the patient's body is focusing on the property of matter called volume. Okay, how much space, though, that amount of particle, that amount of substance, or that tumor takes up, that is called volume. So good job to those who chose volume. Our next question. Which state of matter is characterized by having neither a definite shape nor a definite volume? So no major shape, no specific volume, and the particles are widely spaced and moving freely at high speeds. Is this a solid, liquid, gas, or plasma? I'll give you 1 minute. All right, the state of matter that doesn't have a major or a definite shape or volume, that have particles that are widely spaced and moving crazy all about, is most certainly a gas. So good job to those who chose gas. Let's talk about the other options quick though. A solid, remember, will have a definite shape and a definite volume because those particles are not widely spaced. They're super compact. They're not moving freely. So that just completely rules out a solid. A liquid does not have a definite shape because it just takes the shape of whatever container it's in, but it does have a definite volume because there are a certain number of particles that are there, which means it takes up a certain amount of space no matter the shape it takes on. And the particles aren't really widely spaced. They move kind of freely. They have a little bit of energy, but they're not widely spaced. So that's ruling out a liquid. And then finally, plasma. Plasma does share some characteristics with gases, like not having a definite shape or a definite volume, and it does have particles that move freely. But the key difference about plasma is that it has like these really unique electrical properties and the presence of like charged particles. And we never even talked about that with a gas. And that's just pretty much unique to a plasma. So that rules out plasma. Next question. In healthcare settings, understanding the behavior of substances during phase changes is really important. Which of the following best describes the phase change occurring when an alcohol-based hand sanitizer evaporates from a patient's skin? Okay, so think about the state or the phase that it's in. And then how does it change? What do we call that phase change based on the state of matter it was in and then what it becomes? I'll give you 1 minute to think this through. All right, so when we've got an alcohol-based hand sanitizer, that it comes onto your hands in the form of a liquid, and then we said it evaporates from that patient's skin. So it starts as a liquid and it becomes a gas. And so that term with that evaporation is the phase change vaporization. So awesome job to everybody who shared their answer in the chat. I see some people even working out their thought process saying, I think this is a liquid going to a gas, therefore it's vaporization. So awesome job. But let's talk about why the other options are incorrect. So freezing, option A, is when the alcohol would change from a liquid to a solid. And that's certainly not happening if the hand sanitizer is evaporating off of the patient's skin. It's not becoming a solid. So we can rule freezing out. Option B, condensation, would be the phase change of from like the alcohol changes from a gas to a liquid. And we're not administering hand sanitizer to a patient in a gas form, it's a liquid form. So that rules out condensation. And remember, option C is correct because the alcohol changes from a liquid to a gas. And option D, sublimation, is when the alcohol changes directly from a solid to a gas, but that hand sanitizer doesn't go on that patient's skin as a solid, it goes on as a liquid. So option C is the correct answer there. Last question before we wrap up this section. The question is, which of the following statements are true regarding the densities of solids and liquids? Select all that apply. I'll give you a minute to read through these and choose all of your responses that are true for the densities of solids and liquids. All right, our question was, which of the following statements are true regarding the densities of solids and liquids? Select all that apply. So let's go ahead and click to the next slide, and then I'll just break down each option here. Solids typically have a higher density than liquids due to those closely packed particles. Option A is one correct answer. Remember, solids have less energy, and so particles are tightly packed, making them more dense. Option B is also correct. Liquids can be less dense than solids, depending on the material. Liquids are less dense than solids because, remember, liquids have a little bit more energy, which makes those particles move around a little more freely. They're less dense. Option C, the density of a substance does not change the overall, or does not change regardless of the state. So it could be a solid or a liquid, and that density would never change. But that is completely false. The density would absolutely change depending on that state. So if we compact those particles more tightly together, something is going to be more dense, and that would be the solid state. Whereas we let those particles move around more freely, they're less dense. So the overall numerical amount for density would be less than for a liquid than it would be in the state of a solid. Option D, in general, solids maintain a fixed shape, while liquids take the shape of their container. This is definitely true. Since particles move less freely in a solid, they are more fixed, whereas in a liquid, particles move more freely and take on that shape of whatever container that they're in. Option E, the density of a solid is always greater than the density of a liquid. Option E is true most of the time. Not all states of matter, though, would this be true for. So for example, ice, so solid water, is actually less dense than liquid water. And this unique property of water is what allows for life to exist. And that's a really interesting topic that we're going to get into just a little bit later on here in this webinar. So options A, B, and D are correct for this practice question. Good job to those who chose those. And let's wrap up 3.2. Matter makes up our entire physical world. Matter has a specific mass, volume, and density, no matter the state. The state of matter are solids, liquids, and gases, and the state that it exists in just depends on the energy of the particles. And the states of matter can change. These are called phase changes. And the states of matter will change depending on the amount of energy. So phases can be evaporation, freezing, condensation, melting, sublimation, and deposition. Okay, I'm just reading the chat here quick. Someone had asked if we could go over the previous question again. So I can go ahead and quickly go back here. They had said if we could just go over option E. So the density of a solid is always greater than the density of a liquid. I had said that this is true most of the time, but there are some forms of matter, like in water, for example, where that is not true. The density of solid water is actually less dense than the liquid form of water. This is very unique to just water, but this property allows for life to be able to exist. So I can give more explanation on that topic in a little bit later on in this webinar. So for those who asked, I hope that we can come back to that when we talk about the properties of water and how that pertains to allowing for life to exist. But if that's not enough for you, don't forget, check out our on-demand videos where you can go over this topic at your own pace and get other practice questions around that idea. Okay, moving on to describing chemical reactions. Remember, guys, chemical reactions are going to bring us right back to the idea of valence electrons. So if you want to begin understanding chemical reactions, then you must understand everything there is to know about valence electrons. So remember, valence electrons are the electrons in the outermost shell of an element. Valence electrons participate in chemical reactions since they are the outermost electrons. They're those first set of electrons that another neighboring atom would come into contact with. And these atoms can either lose or gain these electrons, or they can share these electrons. So remember, valence electrons can be lost from an atom, they could be gained from another atom, or they could be shared. And these attributes determines the type of chemical reaction that would take place. And also remember, on the periodic table, you can determine the number of valence electrons just by looking at what vertical column, what group that atom belongs to. So lithium would have 1 valence electron. Neon would have 8 valence electrons. And with each shell, it's trying to become full. So remember how we said that first shell can have 2 valence electrons, but every shell outside of it can hold 8 valence electrons? An atom is going to be completely happy and satisfied if their entire shell can be full. So for helium, it can only hold 2, and it's got to. So helium doesn't want to share, doesn't want to gain, it doesn't want to lose. It's content just the way that it is. A carbon atom has 4 valence electrons. So it could lose 4, but it could also gain 4. So that would require the same amount of energy for both actions, or it could just share to get 4 more. Neon has 8 in their complete outer shell, and so they're full and happy, kind of just like helium. They're not going to want to steal, they're not going to want to give, and they're not going to want to share because they already have 8 to fill that outer shell. So understanding the amount of valence electrons, understanding how many valence electrons could fill that outer shell is essential to you understanding chemical reactions and what type of chemical reactions will take place. So the type of chemical reactions that can take place, or the bonds that it makes those chemical reactions, are called ionic bonds or covalent bonds. Now, ionic bonds are types of atoms that can lose electrons or gain electrons. Remember that word ion? We talked about this in that first section. Ion means that this atom has an overall charge. So if this atom of lithium wants to steal or give an electron away, so let's look back at our periodic table. Lithium is right here. It has 1 valence electron. So if lithium were to lose 1 valence electron, it could lose 1, lose that outer shell, be full and happy if it lost 1, or it could gain 7 to get to 8 to fill its outer shell. Losing 1 is less energy than having to work to get 7. So lithium is going to be more than happy to give an electron away. It requires less energy to do that. Just give my outer electron away, and now what I'm left with is just that inner shell that's full and happy. If I lost an electron, this electron has a negative charge. That means I am now overall positive. I lost some negativity. I lost a negative electron, therefore that makes me more positive. So lithium would be a cation. Fluorine, on the other hand, let's go back to our periodic table. Fluorine is right here in group 7, so it has 7 valence electrons. So fluorine could either take 1 more electron in to its outer shell to make it 8, because remember, each orbital can hold 8 if it's not the first orbital or the first shell. Fluorine can take 1 more and it would be full and happy because it reaches that 8 valence electron, that full feeling. Or it could lose 7 to get rid of that outer shell. It requires way less energy to just take on one versus having to lose 7. So fluorine is really happy to be paired up next to lithium. Lithium wants to give one away. Fluorine is saying, hey, I'll take it. I need one more to completely fill my outer shell. I had 7 and now I gained 1. And since it gained 1 electron, an electron has a negative charge, it has this overall negative charge to it. Fluorine would be an overall negatively charged atom, making it an ion. So an anion. So in any ionic bond, you're going to have this partnership between a cation, a charged atom that really wants to lose electrons, and fluorine, an anion, or any element who wants to gain an electron. So it's a relationship between a cation and an anion. That's what it creates through an ionic bond. And these opposite charges attract through creating this ionic bond. So you really got to understand those valence electrons. You have to know those groups, those periods on the periodic table to know how many valence electrons, how many orbitals or shells are around that atom. Does it want to gain? Does it want to lose? Or does it want to share? So let's move on over to covalent bonds. The term covalent is like that prefix co. So I think of like co-parenting or co-teaching. It means together. And so with a covalent bond, you've got 2 atoms that are sharing electrons together. We're not stealing, we're not gaining electrons, we're sharing electrons. And this sharing, this covalent bond, forms an electron pair. So see these pairs that are situated right next to each other. This overlapping of an orbital from this oxygen, or a shell from this oxygen, overlaps with this outermost shell from a neighboring oxygen. And these electrons in these outermost shells pair up next to each other. It forms an electron pair. Now you can recognize a covalent bond because it will typically occur between non-metals. So 2 oxygen atoms, oxygen's a non-metal, when 2 get next to each other, that would form a covalent bond. Whereas ionic bonds, lithium is a type of metal. And so when a metal gets around a non-metal, like fluorine gas, for example, then it would form an ionic bond. Okay, let's practice. Let's break it down in our own words here. We can do this. Distinguish between covalent and ionic bonds. So take a moment to just debrief covalent versus ionic bonds in your own words. I'll give you 1 minute. All right, distinguishing between covalent and ionic bonds. Oops, let me go here. So ionic bonds form when electrons are transferred, creating oppositely charged ions that attract to each other. Remember, one would be positive, one would be negative. And I see some people in the chat even share that it would be between like a metal and a non-metal, for example. So great job adding that detail into your answer. While covalent bonds involve the sharing of electrons between atoms, and that could occur typically between nonmetals. But the biggest takeaway here is ionic bonds are going to transfer electrons, while covalent bonds are going to share. All right, knowing this information, let's move into chemical equations. So chemical equations are chemical reactions that are expressed as chemical equations. So it's just a chemical reaction that looks like a chemical equation. So you've got reactants as your starting materials. I've got coded here in blue. This would be, in our example, like sodium mixing with chlorine. These are our starting materials. These are called reactants. And when these two are near each other, so see if you can determine, is this an ionic bond or would this be a covalent bond? We've got a metal with a non-metal. Sodium has 1 valence electron, chlorine has 7. Hopefully in your mind you're thinking about an ionic bond here. So when these two get next to each other, a chemical reaction is going to occur, specifically an ionic bond. And it produces products. Products are the ending materials, and they're on that right side of your chemical equation arrow. So the products here are in red. Sodium and chlorine are officially bonded to each other due to that transfer of an electron. But these reactions can be represented by a reversible arrow. So sometimes you'll see just a forward arrow that would be irreversible. Can't go back to its original starting pieces. But sometimes chemical reactions can go both ways, meaning it is reversible. So keep a close eye on that when you're looking at your chemical reactions. Okay, so most times when looking at an equation, you'll not only see the element symbol, like C for carbon, H for hydrogen, but you'll see various forms of numbers next to those symbols. So these can either be subscripts, sub meaning like below. So if you've got a number down below the element symbol, this is called a subscript. This is indicating to you that there are 4 of whatever element that subscript follows. So this subscript 4 follows a hydrogen element symbol. So that's indicating that in this molecule, there are 4 hydrogens for this 1 carbon. We don't use a subscript to ever refer to one that is representative of itself just by the presence of that C, that 1 carbon. So if there's not a number associated with it, you can infer that it's just one carbon in this molecule, for example. But in this molecule overall, there's 1 carbon and there's 4 hydrogens. But you can also come across coefficients or moles. Now, the coefficient or the mole will be in front of that entire molecule. So notice how it's completely in front of any element symbol. And the coefficient represents how many molecules or moles there are in total. So not just each individual element. It doesn't just follow an individual element. It's saying there's 2 of everything that's here. So there's 2 sodium chlorides is what that's referring to. And here's our visual to show 2 NaCl molecules. So when balancing equations, which we're going to get into next, you can only change the coefficient. Keep that in mind. When we balance chemical equations, you can only change the coefficient, that number out in front. You can only manipulate how many molecules overall you have, not each individual element itself in that molecule. So we're going to do this together, balancing equations, but the law of conservation of matter states that matter cannot be lost and it cannot be gained. So in a chemical equation, whatever number of stuff you're starting with, you have to make sure that you're ending with that same amount of stuff because matter can't be destroyed and matter cannot be created and come out of nowhere. So balancing chemical equations helps you recognize, do I have all the right stuff I need in order to make the product I want? And vice versa, if it's a reversible chemical reaction. So step 1, We're looking at what the equation is. It's unbalanced right now. We're looking at a hydrogen molecule, and there's two hydrogens in this molecule here. We've got two oxygens that it's going to be added to. But in the end, we're making H2O, which is water. So start by just taking inventory. What do I have on both sides? How many of each do I have on my reactant? How many of each do I have on my product side? And I've got some visuals to help us with this guided practice. So let me switch to the next slide. Here's what I mean by taking inventory. Check the number of atoms of each element. There are two hydrogen atoms on the reactant side, because that little subscript 2 tells us that there are two hydrogens here. How many hydrogens then do you have on the product side? Should be equivalent, but maybe it's not. So it says H2O. We've got this subscript 2 following the hydrogen. That's telling us that there are two hydrogens here on the product side. So hydrogens are actually balanced right now. We've got two hydrogens on reactant side. We have two hydrogens on the product side. That's looking good. Now let's move on to oxygen. There are two oxygen atoms on the left side from this O2 subscript. And we look at the oxygen on the product side. We've got one oxygen. There's no subscript there to follow it. So there's only one oxygen on the product side. And we've got two oxygens on the reactant side. That's not balanced. So to balance your oxygen atoms, you have two on the left, you've got one on the right. What can you do? What's a basic mathematical step you can do with one oxygen and you need to get it up to two? You can only mess with the coefficient out in front of this entire water molecule. So to balance that oxygen atom, you will need to add two molecules of H2O. You'll need to put a 2 in front of this water molecule because you can only manipulate the coefficients. You will need to add 2. So let me go to my next slide to show you what that looks like. Okay, here's that original step we had where it was unbalanced. We have one oxygen, we have 2 over here. We need to make this side also have 2 so that we've got 2 oxygens on the product matching the number of oxygens on the reactant side. And we can't mess with subscripts. All you can change are coefficients. So we're going to put a 2 out in front of that H2O because 2 also applies to the oxygen. So we've got 2 oxygens now on the product side. But that 2, it's like the distributive property in math. That 2 also applies to your hydrogens because this is affecting the entire molecule. So now, because you've got 2 water molecules, your oxygens are great. You got 2 oxygens on your product, you got 2 oxygens over here in your reactants. But now you've also altered the number of hydrogens in your product since you added that 2 coefficient. 2 times 2 hydrogens for each water molecule equals 4. 2 times 2 equals 4. And in our visual, we've got 4. 1, 2, 3, 4. So our oxygens are balanced, but now our hydrogens aren't balanced. We've got 4 hydrogens on the right-hand side, and we've only got 2 hydrogens on the left-hand side. You can only change the coefficients. So what we need to do now is balance out this hydrogen. We need to make the number of hydrogens on our reactant side match the 4 hydrogens on the product side. So if you only have 2 hydrogens, we need to get to 4. How can we take 2 and get to 4 using a multiplication tool for that coefficient? So hopefully you're thinking about 2 times 2 equals 4. So we're going to add, here's that third step broken down for you. We're going to add a 2 coefficient out in front of that H2 molecule, and 2 times 2 equals 4 hydrogens. So let's double check all of our counts. Take inventory after each step to make sure you've got what you're intending with your math. We've got 2 times 2 equaling 4 hydrogens on our reactant side. And on our right-hand side, we've got 2 molecules of H2O. 2 times 2 H's is 4 hydrogens. So 4 hydrogens also fits on our product side. That's balanced. Let's take a look at oxygens. There's no coefficient out front of this O2, so that's just meaning there's one. There's one O2 molecule. So there's our 2 oxygens right here. And on our product side, when it's making water, we have 2 oxygens as well. We are completely balanced. So we have proven through this chemical reaction, matter cannot be gained or lost. We've maintained the law of conservation of matter, and we're making sure that if you want to end up with 2 water molecules, these are the number or the amount, the moles of stuff you have to start with in your reactants. So chemical reactions, I like to think of it as like a mind game, a little puzzle with just some basic multiplication math skills. I think it's fun to kind of work it out that way. Hold on, I got a question in the chat. Okay, great question here. They said, why can't you put the coefficient 2 in the oxygen on the product side? So just to clarify why you can't put a 2. See how oxygen here, it's a part of this entire H2O molecule. You cannot separate this oxygen away from these hydrogens because on the product side, they're bonded together. So we can't put a 2 coefficient only in front of the oxygen. There's no space there for it because it's literally bonded to those hydrogens in water. So whatever you do or you want to do to just oxygen, it's going to affect the hydrogens because it's bonded in that molecule all together as one. That's part of that product side. Hopefully that answered our question in the chat. If not, feel free to message me privately and I can chat with you after as well. And remember, we can break this down a lot more in detail for you and at a slower pace in our on-demand videos. Balancing chemical equations, if this is the first time you're seeing it, this can feel overwhelming at first, and I completely understand why. So if you need that extra practice, hit up our on-demand videos, or you know what? Go ahead and contact our tutors. Shelly is our science tutor right now. She's a fantastic educator. She was an educator for many years. She would be able to help you one-on-one directly, more so than what even our on-demand videos could. So there's a little plug to go look at our tutor schedules as well. Let's do another one though. Okay, so that was guided practice. This one I don't have all the visuals in here for you, but feel free to draw those visuals for you in your notes as we work out these steps together. So this is balancing the combustion of propane. Propane is our C3H8, so this is one whole molecule here. So there's only one coefficient, and one coefficient in front of that molecule will affect everything in that molecule. So remember my tip, take inventory. How many of each atom do you have on each side of your chemical equation? So on a reactant side, we've got no coefficient, so we can just assume everything is one molecule. So in one molecule of propane, there are 3 carbons, 8 hydrogens, and that will react with oxygen gas, and there are 2 oxygens in that one molecule of oxygen gas. So we've got 3, 8, and 2. Let's check out the other side. Through combustion reactions, it will make carbon dioxide and water. But remember, law of conservation of mass. We can't lose, we can't gain. We have to make sure all of our pieces are still accounted for, even though we're altering their form. So on the product side, you've got 1 carbon. There's no coefficient. There's no subscript. So we've just got 1 carbon. So already, hopefully you're seeing we're unbalanced because there's 3 carbons over on the reactant side. But in the end, you only end up with 1. Matter doesn't disappear. Where'd the other 2 go? We have to balance this equation. Oxygens, there's 2 in CO2, but there's also another oxygen in this water. So 1 over here plus your 2 here, that equals 3. 3 oxygens on the product side. We've only got 2 oxygens on the reactant side. Something's not equaling out here. And then take inventory of your hydrogens. There's 8 hydrogens on the reactant side, and you see 2 hydrogens in this water molecule on the product side. So nothing is balanced. Let's go ahead and work out our steps. So to balance the carbon atoms first, let's do carbons because it's listed first here. To balance the carbon atoms, you need to put a coefficient of 3 on this product side because we've got 3 carbons on the reactant side. We only have 1 on the product side, so a coefficient will multiply through. So 3 times 1 is 3. If we put a 3 out in front, I'll go to the next slide so I can show you that. If we put a 3 out in front, now our 3 carbons will match our 3 carbons on the reactant side. So let's go through and take inventory. Not just carbons are going to change. We want to make sure we understand the full picture here. So on the reactant side, we've got 3 carbons, we've got 8 hydrogens, and we've got 2 oxygens. We did not add a coefficient to anything on the reactant side, so nothing has changed on the reactant side. We did add a 3 coefficient to the CO2 carbon dioxide molecule, and that 3 will distribute through and affect not only the carbon, but it will affect oxygens as well. So we've got 3 carbons, that matches. But that 3 will also affect the oxygen. And there are 2 oxygens there. So 3 times 2 is 6. But we also have another oxygen in our water. Don't forget about this guy over here. 6 oxygens in CO2 plus the 1 oxygen in our water is a total of 7 oxygens. Not balanced when we compare to our reactant side. 2 versus 7. Still not balanced. Carbons look good, but oxygens are still not good. How about hydrogens? Hydrogen, there are 2 here on the product side, and there are 8 on the reactant side. So not balanced with oxygens, not balanced with our hydrogens. So what can we do? Let's go ahead and make sure that we look at all factors with our multiplication to figure out where to go next. So let's balance the hydrogens. To balance the hydrogens, we've got 2 over here. We need it to get to 8 to match. So how can we get from 2 to 8? Hopefully you're thinking multiplication. Multiply what by 2 to get to 8? So to balance the hydrogen, let's put a coefficient of 4 in front of this hydrogen so that there will be 8 hydrogens on the product side to match the 8 hydrogens on the reactant side. So I'm going to move to the next slide here to show that coefficient change. So our 4 is now added. 4 times 2 hydrogens equals 8 hydrogens. That matches our 8 hydrogens on the reactant side. Hydrogens are looking good. But this 4 coefficient will distribute through and also multiply your oxygen. So remember, it's a puzzle. It's a mathematical puzzle. 4 times 1 oxygen is 4 oxygens total in water. But let's not forget our 3 times 2 oxygens, which is 6 in our carbon dioxide. So we've got 6 oxygens in our CO2 plus our 4 oxygens in our water. 6 plus 4 is 10. 10 oxygens. Do we have 10 oxygens on our reactant side? Definitely not. We've only got 2. But I hope your brain is already thinking, to get from 2 to 10, what's a coefficient you can put out in front for simple mathematical representation? So we need to put a 5, a coefficient of 5 out in front of this O2 reactant molecule because 5 times 2 will equal 10. So I'm going to go to that next slide to show that coefficient. So 5 times 2 equals 10. Let's go ahead and take inventory of each one of our atoms on both sides and see where we're at. For carbon, on the reactant side, we've got C3. There's no coefficient there, so you can just assume it's one propane molecule. So 3 carbons on the reactant side. How many carbons on the product side? 3 coefficient times 1 carbon, that's 3, 2. That's looking good. Hydrogens. Hydrogens have 8 on the reactant side, and hydrogens on the product side are 4 times 2. That also is 8. So hydrogens are balanced on the reactants compared to the products. Oxygens, let's take that last bit of inventory here. We've got a coefficient of 5 out in front of that oxygen reactant. 5 times 2 is 10. And oxygen on the product side, it's just divided up into 2 different parts. So make sure you're factoring in oxygen in both types of molecules. So you've got 3 CO2 molecules. So 3 times 2 oxygens is 6, plus 4 oxygens in your water. 6 plus 4 is 10 oxygens in the end for all product material. And there are 10 oxygens in all of your reactant material. So we are now completely balanced. We have the same amount of every element on both sides. So just again, I know balancing equations, it's time consuming, and you're probably going to want more practice with this. So if you need to check out our on-demand videos, please do so and work these out at your own pace, or better yet, contact our awesome science tutor, Shelly. She can squeeze you in, and I'm sure she'd be so happy to work out these problems with you. We're going to move on. So the types of chemical reactions that can occur. You can have a synthesis chemical reaction. This is where 2 compounds interact to form one new compound. They make one product. Okay, so 2 separate reactants synthesize, they make one final product. But another type of chemical reaction is called a decomposition reaction. And this is a reaction that occurs when a compound breaks down into 2 or more compounds. So see how that reactant is one molecule, and it decomposes into its individual subparts, its individual elements. That's decomposition. Single displacement is a reaction that occurs when a new compound is formed when one part of a compound is substituted for another part of a compound. So see how A, B were together here, but we're actually going to swap out that B and add the C to the A. So it actually makes 2 new compounds in the end, even though you just swapped out one single element. That's called single displacement. A different type of chemical reaction you'll come across is called a double displacement reaction. And this is a reaction in which the cationic or the anionic species switch. Okay, so we've got that positively charged ion or the negatively charged ion. They're just going to switch places, creating 2 new products. So instead of AB being bonded together, we're going to bond A with D, a completely separate component from a different molecule. And then their complementary parts are also going to bond together. So B and C will find each other and bond. So this is called a double displacement. All right, let's take a minute to check in. Which of the following are covalent bonds? Select all that apply. Is it sodium and chlorine, carbon and oxygen, magnesium and oxygen, or hydrogen and nitrogen? You're going to want to think about, are they metals? Are they nonmetals? How many valence electrons? Factor all of that into your thinking when you're determining which ones are covalent bonds. All right, everybody, to figure out which are covalent bonds, I think the quickest way to do so is to rule out which are metals, because remember, covalent bonds are going to form between non-metals. So which options have a metal in it, and throw those out. So you have to be familiar with your properties on your periodic table. We keep coming back to that periodic table, you guys. You got to understand all the patterns in that periodic table. So our correct answers are B, carbon and oxygen, two non-metal atoms, and D, hydrogen and nitrogen, again, two non-metal atoms. Option A, sodium and chlorine, can be ruled out because sodium is a metal. And so sodium and chlorine would form an ionic bond. Sodium has one valence electron, chlorine has seven. We talked about that in one of our examples. So sodium, being a metal, is really willing to lose that valence electron, and chlorine, having seven, so close to that eight, wants another valence electron desperately. And so they're going to transfer electrons. That's not what a covalent bond is. That's an ionic bond. Covalent is sharing electrons. The same reasoning can be applied to option C for why option C is not correct. Magnesium is another metal, and oxygen is going to be better off energy-wise to gain the electrons that magnesium is willing and happy to get rid of. So if you see that metal with a non-metal, you can rule that out as a covalent bond. Next question. Go ahead and match the chemical reactions to their correct name or type. So I've kind of scrambled our visual here. Go ahead and drag an arrow or write them out in your notes. Which representation, which chemical reaction or chemical equation matches with the correct chemical reaction name or type? I'll give you 1 minute to sort these out. All right, I think the best way to show you which chemical reaction name and how it matches with the chemical equation itself is just to show you the arrows, and then we'll talk about why those arrows are pointing to what they are. So let's start with single displacement. The single displacement reaction is a reaction that occurs when a new compound is formed just by substituting one part of a compound for another. So when we look at the equation, it matches to. We had AB next to a molecule C, and we swap out the B part for the C. So C is now attached to the A, leaving B to be solo. So we're just swapping out one part and bonding that new part to the A, creating new products in the end. That's called single displacement because we just swapped out one component of that original molecule for the neighboring molecule. Synthesis is when we have two separate reactants and we combine them. We make one molecule from those individual two that we started with. Double displacement or replacement is going to be when you have a reaction that switches places, creating two new products. So the double replacement reaction swaps the cation or the anion. It swaps two things at a time, not just one, but two things at a time. Okay, and then we end up with our two new products. If we didn't swap two at a time, no new compound would be formed here. So that double word is really key because we're swapping two components at the same time, creating two new products in the end. And then we've got decomposition, which is when we have one molecule and we decompose, we break them down into their individual chemical reacting components. All right, we've wrapped up 3.3, which is our chemical reactions. So remember, valence electrons are electrons in that outermost shell. And these valence electrons are absolutely responsible for the chemical bonds. Is it going to be ionic? Is it going to be covalent? The bond that takes place is because of the valence electrons. So with ionic bonds, remember you've got exchanging or transferring of electrons that leaves an atom with an overall charge in the end, which we call an ion. It either ends up negatively charged or positively charged. Whereas covalent shares electrons. We're not ending up with an overall charge of an ion in the end. We're just sharing those electrons. Reading chemical equations depends on your ability to distinguish between subscripts and coefficients, and it's just a math game, a mathematical math game with figuring out, do I have all components in the reactant side equivalent in the product side? Because the law of conservation of matter states we can't gain energy, or we can't gain matter, and we can't lose matter. We have to account for all at all times. So with balancing chemical equations, again, just make sure that you're always accounting for all parts of matter. And there are types of chemical reactions that you are balancing, that you're making sure all parts of matter are represented in. You can have a synthesis reaction, a decomposition reaction, or a single or double displacement or replacement reaction. Those words are interchangeable. All right, we are moving on to conditions that affect chemical reactions. So now that we know how to represent chemical reactions, we know that matter can't be created or destroyed. We know there are different ways to combine or to decompose or break down and rearrange things in a chemical reaction. What are things in our world, either in our natural world, like in our bodies, or in our physical world around us, that affect these chemical reactions? Can we speed them up? Can we slow them down? So remember the basics of a chemical reaction. We've got reactants, which are our starting materials, and we have products, which are our new substances formed after that reaction. But sometimes in a chemical reaction, our body works really hard to reach this state of equilibrium. We talk about this theme quite a bit in anatomy and biology. Except for equilibrium, we may use the term homeostasis. So these are going to be chemical reactions that take place in your body where we try to get the amounts of our reactants to stay constant when it would compared to the amounts of our products. So reactants, we want to balance out the products, and with products, we want to balance out the reactants in a reversible chemical equation. And like I said, this takes place all the time in your body. How can we maintain homeostasis? How can we keep this balance between reactants and products, especially when we look at metabolic processes in our body? However, the body will often prevent true equilibrium just to keep these processes moving in the direction needed for survival. So some classic examples beyond metabolic processes are oxygen and hemoglobin binding, and calcium ions and muscle contraction, for example. Your body wants to reach a state of equilibrium, but we also have to make sure we keep those chemical reactions moving forward so that your muscles don't contract where we want those muscles to contract, for example. So the factors that do influence the reaction rate are concentration, pressure, temperature, and catalysts. Understanding factors that influence your reaction rates, you guys, are so important for you as future nurses. Many medications rely on specific reactions within the body to be effective. And so as future nurses, you need to understand how factors like temperature, concentration can impact the patient's overall ability to absorb that medication, to metabolize and break down and use that medication so that it is effective. So let's talk about each factor. With concentration, concentration simply refers to the amount of a substance in that given volume. This sounds just like density, you guys. Concentration is density. How much stuff of that substance is in a given volume. When there are more particles in a given amount of space, the more collisions will occur. If we pack more particles in to the same amount of space, we don't change that amount of space, there's more opportunity for collisions, and those collisions will lead to chemical reactions. So adding like a higher concentration of something will increase the reaction rates. This is why you would like up a dosage of a medication. You're introducing more particles of that substance to the patient's body to increase the likelihood that those particles chemically react with what it needs to inside of the body so that it's effective. Another factor is pressure. Pressure refers to the force exerted on a surface by this continuous collision of molecules. So the higher the pressure you have, that means that you're increasing the concentration of all of those gas particles, for example, leading to more frequent collisions and a higher reaction rate. If you reduce the pressure, if you lower the pressure, you are increasing the amount of space, which slows down that reaction rate because these particles now are not going to come into contact with each other as often. They're not going to collide as often. So that's going to slow down your chemical reaction. So keep in mind, pressure is also going to impact like solubility of your gases in liquids. This is really important for like the concept of IV therapy. So nurses should just be really cautious with pressurized solutions and be aware of how these dissolved gases might behave when administered to patients in an IV. Because if you mess with the pressure, and since the tubing of the IV is going to create a pressure because of the volume, you're influencing the reaction rate of that medication. Moving on to temperature. Temperature affects the reaction rates because we're increasing the amount of energy in our molecules, specifically kinetic energy, which is the energy that allows the ability for movement. So generally, high temperatures will increase the speed of all particles. So if these particles are moving around more often, they have greater chances of colliding and having that chemical reaction. Our final factor here is a catalyst. A catalyst is a substance that speeds up a chemical reaction because it reduces the amount of energy it needs for that chemical reaction to start. But the cool thing about catalysts is that that catalyst itself is never permanently changed. It's not broken down in that chemical reaction. It can just continue to be reused over time. So an example of a catalyst, like enzymes. Enzymes in your body are proteins that speed up these natural reactions in your body. So for example, you have amylase. Amylase is an enzyme found in your saliva. And this is a catalyst that helps to break down starch into sugars. That starts in your mouth, but also continues on into your digestive system. Amylase itself will never be broken down. It can continuously be reused, but it's reducing the amount of energy your body needs to convert that starch into sugar, speeding up that reaction because it doesn't have to wait around for more energy to do so. So just be aware as a future nurse how different drugs interact, because some reactions can enhance chemical reactions like a catalyst, while some things that you introduce to the body can inhibit chemical reaction. So some medications can speed up activity, some medications can absolutely slow down or lower the effectiveness. And knowing those reaction types helps you manage dosages and helps you to avoid any kind of harmful interaction. All right, our first practice question for this section: which of the following influences the rate of chemical reactions? Select all that apply. Is temperature a factor? Is concentration, catalyst, pressure, and water? Which of these are factors that influence the rate of chemical reactions? I'll check in with you in 1 minute. Thank you to those who are participating in the chat. I see your responses and they are all correct. So the factors that influence chemical reactions are temperature, concentration, catalysts, and pressure. Leaving out water. Water is just a universal solvent that is present in every living thing. The presence of water is not going to alter the rate of your chemical reaction as a major factor. Next question. How does a catalyst specifically affect the chemical reaction rate? Does it slow down the reaction rate by decreasing the energy? Does it slow down the reaction rate by increasing the energy? Does it speed up the reaction by decreasing the activation energy? Or does it speed up the reaction by increasing the energy? Give yourself 1 minute to think about how a catalyst affects a chemical reaction. Okay, catalyst affects the chemical reaction rate by speeding up the reaction because it decreases the amount of energy necessary for that reaction. So if we take away some of the energy that's needed for that reaction to be carried out, the reaction can go on quicker. So it would speed up that reaction overall. So option C here is our correct answer. If the energy was increased, for example, so if increased energy was needed to activate that chemical reaction, like some of these options say, it like increases the activation energy. If that were true, that means that your body would need even more energy to carry out that chemical reaction, which takes some time to acquire that extra energy. So that certainly would not speed up the chemical reaction. It would slow it down. Okay, it would slow it down. And that's not the purpose of a catalyst. A catalyst is to help speed up the reaction by decreasing the amount of activation energy. I hope that helps some of our people over in our chat on YouTube who wanted to understand better about reducing energy and that meaning. And remember, when it comes to these factors, if you need a like a slower pace, different examples, it broken down into greater detail, that's where our on-demand videos are essential for each individual learner. So don't forget to check those out if you want to go into these factors into greater detail. Le Chatelier's principle is a fundamental concept in chemistry because it says that if a system at equilibrium is disturbed, the system will shift in a direction that will kind of counteract or offset that disturbance to get back to equilibrium. So that sounds like very sciencey, using all those different terms. Basically, it's just saying if something's disrupted in your body is going to do what it needs to try to get back to that balance. So if something is like added to your system, okay, well then how can we get rid of that efficiently? If something is not as concentrated, you're really low on something like glucose, you got some low blood sugar. How can we add to that? How can we improve that glucose level to get back into balance? So just remember Le Chatelier's principle. If you change any conditions like concentration or pressure or temperature in your patients, that reaction that was not balanced or will try to get back to its balance. It will try to readjust all of its levels to minimize that change. So remember, we talk about that theme called homeostasis in biology. We talk about homeostasis in anatomy because that's just how our bodies function. And understanding that your body is always trying to maintain balance, even at the chemical level, is really essential for you to be successful as a nurse. So a review of 3.4. Within chemical reactions, you'll always have reactants and we'll always have products. And when it comes to an equilibrium, trying to maintain this balance, there'll be this back and forth play where we've got the amount of reactants should equal our products, but then the amount of products can be reversed and equals the reactants. Our body's always trying to maintain equilibrium at that chemical level. And so these balanced factors influence the reaction rate. So those factors are concentration, pressure, temperature, and catalyst. These factors influence reaction rates by speeding them up or sometimes slowing them down. And when you alter those conditions, remember Le Chatelier's principle, your body is always going to try to get back to that homeostatic equilibrium state. Moving on now into properties of solutions. I can see based on our time right now, we're going to go a little bit past 8 o'clock, but that's okay. If you have to hop off here by 8 o'clock, don't forget about all of the wonderful things we offer at Archer Review for you to help you with your TEAS exams and to also take that survey. I've got a QR code for you so that you can leave some feedback. What worked really well for you? What didn't work so well for you? This is our first chemistry webinar in a while. It's my first chemistry webinar with you guys. How can I improve to better suit your needs in this 2-hour time crunch breaking down chemistry as a crash course? So don't forget to leave me that feedback if you have to hop off here in a few minutes, but we'll continue and we'll go a little past 8 o'clock. So moving into properties of solutions. A solution is a type of mixture where 2 or more substances are evenly mixed together. So within one solution, you're going to have those 2 things, these 2 substances that are mixed together. You'll have a solvent and a solute. A solvent is the substance that does the dissolving. A solute is a substance that gets dissolved, and it gets dissolved by the solvent. You can normally tell the difference because the solute is present in smaller amounts than your solvent. And a universal solvent is water. So if you're trying to dissolve something into water, the solute would be that something, like you're trying to dissolve salt maybe into water. So the solute would be salt, the solvent would be the water. It's what does the dissolving. So that makes up every solution, a solvent and a solute. But when it comes to the solvents or the solutions and the solutes, you've got solubility rules. And this is telling you how well a substance like a solute can be dissolved in another solvent. Keep in mind, like dissolves like. So if you put a solute that has similar chemical properties into a solvent with like chemical properties, those things are going to really jive together and they will dissolve one another. Whereas things that are totally opposites from each other, you know, the saying like oil and water don't mix because they're completely opposite chemical properties. So when things aren't like each other, they're not going to dissolve into each other. They're not going to be very soluble. So let's bring it back to some of the molecular properties. Some solutes are going to be hydrophilic, and this term hydrophilic, I've got a little heart next to it. When we break down the word, we've got the prefix hydro. Hydro refers to water. Philic refers to like. So this means water liking or water loving. So I put a little heart next to that to help you remember that if a solute is hydrophilic, it's going to love water. So if we've got a solute that's hydrophilic in water, it's going to dissolve well in water, no problem. And what makes it like water so much? Well, it's due to the chemical properties of being polar. So polar, you hear the word polar, it makes me think of like North Pole or South Pole, like opposite ends, if you're following me with that, opposite ends of the globe. So like what's opposite ends of this molecule? I'll get to the point. In our molecules, we talked about how electrons exist around a molecule or around like a nucleus. If you have a molecule that have like a strong pull on electrons, so like oxygen wants two more valence electrons to have that full outer shell. And so it's going to take those electrons from hydrogen to a degree. It's going to unequally share them. It's going to draw those electrons tighter to itself because it loves those electrons. It wants two more so desperately, it's going to naturally draw and pull those electrons into itself closer and tighter, causing there to be a slightly negative charge on one end of this water molecule. And that leaves hydrogen. It's still there. It's bonded to the oxygen. And the hydrogen still has an electron attached to it, but it's like this unequal sharing. That electron that hydrogen's able to share with oxygen, oxygen's really pulling on it. It's like tug of war. I'm pulling that electron closer to me. It's still attached to you, it's still in your outer shell, but it likes me better. I'm yanking on it harder, and so it's closer to me than you. And so that leaves the hydrogen side of water to be slightly more positive because that electron is going to be drawn closer to the oxygen. So in one molecule, you're going to have one end, one pole, that is going to have an opposite charge than the other end of that molecule. So one end of that molecule is going to be positively charged. One end of this molecule is going to be negatively charged. It creates this polar, this opposite charge effect. And because it's polar, it allows it to be water loving. Why? Because water is the same way. Water is also polar. So any molecule you come across that is polar, that has this slightly positive end of a molecule and the other end of the molecule slightly negative, it's going to dissolve so well in water because water does the same thing. So if molecules are polar, they're going to be hydrophilic. But some solutes are going to be hydrophobic. Hydro meaning water, phobic meaning fear of. It hates water. It's water fearing. It does not dissolve well in water. But why? Because it's non-polar. So this is because the electrons are equally shared. Take a look at our O2 molecule down here. You don't see any positive or negative visual around this molecule because there is no positive or negative end. All of these electrons are distributed equally. And because they're equal, there is no pole. It's non-polar. This would be like oil, for example. And so this O2 molecule is nonpolar. All electrons are shared equally, doesn't have a slight charge. And because of that, it's not going to mix well in water because water is polar. And so understanding whether things are polar or nonpolar based on electrons, based on valence electrons, and those chemical properties that we covered in the first two sections of this webinar helps you to understand and make predictions about certain types of medications or substances that will dissolve well in different parts of the body due to its polar or nonpolar or hydrophilic or hydrophobic nature. So if water is such a common solvent, it can either dissolve well with some things or dissolve well or not dissolve well with other things. Let's bring it back to those unique features that allow for life to exist that I talked about at the start of the webinar. And I said, hey, we're going to come back to this. Don't you worry. So here it is. Water is such a unique substance, you guys. Water is truly essential for life. And here's the chemistry behind why. So we know water is polar because of its overall molecular structure. We've got two hydrogens, we've got an oxygen, and because oxygen is very electronegative, meaning it's going to pull those electrons, it wants that negative charge. Whereas hydrogens, oh gosh, take that electron. I mean, don't take it, but like share it. I'm happy to give you more of it. It has that polar opposite charge nature. We've got one end of the water molecule that's just positive, the other on which is negative. It has this uneven distribution. Because of that structure, polarity affects water and how it allows for life to exist. So, for example, hydrogen bonding is playing a crucial role here for supporting life on Earth because it influences the properties of water and the structure of all biological molecules. So here's how hydrogen bonding contributes to the all functions for life. It allows for high specific heat. It allows for cohesion, adhesion. Oh, I've got high specific heat on here twice. It's really important, guys. But it allows for density and for it to be a universal solvent. And so the hydrogen bonds, I've got an arrow over here. The hydrogen bonds, like, isn't really a true bond. It's this dotted line. It's like just an attraction. It's the attraction from one hydrogen in your water molecule, which is electropositive, being attracted to a neighboring oxygen, which is electronegative. Remember that that affinity for electrons. Oxygen wants to be attracted to other electrons. And so who's it going to buddy up next to? A part of another molecule that wants to get rid of its electrons. So there's just this attraction here. It's not a true bond, but there is an attraction there, making them like get really buddy and close to each other. That's hydrogen bonding. And so hydrogen bond, this bond right here, this affinity for each other, this drawing to each other, allows for water to absorb and retain heat, which stabilizes temperatures not only in your body, but in your environment. So if water is able to retain heat or to stay cool and not like heat up really fast, you've all experienced this. Imagine like a really hot day and you're a kid and you have the ability to go to a lake, a pond, a river, a swimming pool. That's what you're going to do when it's 100 degrees out because that water feels nice and cool. It takes a long time for that water to really heat up to ever become anything close to, its surrounding temperature. And this is also why coastal cities feel so nice and breezy because they're next to large bodies of water that help to absorb and retain that heat from the environment. And water having that high specific heat capacity, that's able to be possible because of this hydrogen bond attraction here. Okay, another unique property for water is cohesion and adhesion. So water molecules are attracted to each other. This is called cohesion. So look at that prefix co. It's bonding and attaching to each other. But water can also adhere to other substances because of its hydrogen bonding. So if it adheres, adhesion, it's sticking to something else. If it's cohesive, which water is, it's sticking to itself. And these abilities are vital for processes like transportation of water. In plants, for example, cohesion helps transport water from the roots to the leaves due to capillary action. We have capillary action in the human body too because of our capillaries, our blood vessels. And then with cohesion, we also have this unique factor called surface tension. So the cohesive forces of being able to stick to itself allows for small little organisms to walk on water, influencing the water's interaction with other surfaces. Okay, water is the only unique substance where the molecules become less dense when it becomes a solid. Remember, we talked about that briefly in our question about solids versus liquids when it comes to density. When it comes to solids versus liquids, almost everything else becomes more dense as a solid. They become more packed together. Water is the one unique substance where it's literally the complete opposite. As water becomes ice, a solid, those particles actually become less dense But because of this unique property, you guys, this allows for ice in ponds and lakes, for example, to rise to the top and float. Ice, as a solid state of water, is less dense, so it floats. If ice, as a solid, were more dense than a liquid, ice would sink to the bottom, and then life would not be able to exist in our bodies of water because our large bodies of water would just freeze from the bottom up. Life would not continue to be able to exist. So, because water has this unique property of becoming less dense as a solid, it allows for life to exist. How cool is that, you guys? Lastly, water is a universal solvent. So water's ability to dissolve such a wide range of substances due to its polar nature, again, because of hydrogen bonding, makes it a really excellent universal solvent. All right, moving on to concentration and dilution. When we talk about solutions, we can mess around with how concentrated is that solution or how diluted is it. So a concentration tells you how much of a substance or the solute is in a solution. So if you want to make salt water that you want to gargle because you've got a sore throat, do you want like just like a little bit of salt, a lower concentration? Or are you going to put even more salt? How much can you handle in your solution to gargle and make the back of your throat feel better? You would increase the amount of salt, which would increase the concentration. And then diluting is just the opposite then. So dilution means you're adding more of your solvent to your solution, making your solute less concentrated. So maybe you try to gargle that salt water and oh God, you're gagging. You just can't take it. There's too much salt in there. So what do you need to do to offset that? You just add more water. You add more of your solvent and it dilutes your solution. So you can play around with this concentration versus dilution, but there's many different units to express that concentration. And so there's, again, different units you'll come across. Most of the time you'll see like grams per liter. For example, it'll tell you how many grams of a solute are in each liter of your solvent. But even within grams and liters, you can have different measurements within that. So you can have like a milligram per deciliter, for example. But a classic example of concentration is going to be gram per liter. Okay, the types of solutions you can run into. This unsaturated solution means that you just don't have a whole lot of solute dissolved. So there's way more solvent. You just don't have a lot of solute. It's an unsaturated solution. Your solution could handle more solute. It could dissolve more. You just haven't really met that maximum amount yet. A saturated solution is that sweet spot. It's the maximum amount of a solute that can be dissolved in that solvent given the temperature you're working with. And then a supersaturated solution is when you've added way more solute than is able to be dissolved. So some of it will dissolve and then you'll see that solute fall to the bottom maybe, or if it's less dense than water, maybe it floats to the top, but it's not able to be dissolved. You still see that solute floating around in your solvent over time. Now, when it comes to the way your body will move solutions in and out of different parts of your body, it depends on the type of transportation. So passive transportation is one way in which substances will move throughout your body without using energy. This is really key to understanding passive transport. And I always tell students, like, think of the word passive. Like if you're passive in nature, you don't normally like confrontation. So you just don't invest energy into that situation. You let things go. You don't really confront it, right? You're not giving energy to it. Keep that analogy in mind when you hear the word passive transport. It's transportation. It's the movement of stuff but you're not using energy to do that. It doesn't cost your body anything. And your body utilizes passive transportation to move solutes and solvents around all the time. Here's two major ways that passive transportation is used. First is diffusion. Diffusion is the movement of any kind of molecule, so like ions, potassium, sodium, glucose, any kind of molecule. It's the movement of a molecule from an area where it's highly concentrated into an area where it's lowly concentrated. Okay, a great example of this outside of your body is like a Scentsy or like spraying perfume or a room spray. As soon as you spray it, all of those perfume molecules are densely concentrated right outside of the bottle. And as time goes on, those particles spread throughout because remember, it's now taking the shape of like a gas. It's evaporating from a liquid to a gas. And those particles are moving like crazy. They're moving freely. And because they're doing so, they're moving from an area where they were highly concentrated and they're moving into an area where there's not as many. That concept, whether it's in your body or outside of your body, that's high to low concentration. And when it's inside of your body, it's called diffusion. Okay, so movement of molecules from high to low concentration is diffusion. Now, when we apply that same concept, but only to water, nothing else, no sodiums, no potassiums, no glucose. If we're talking about water, moving from high concentration to low concentration, that is called osmosis. It's the same exact idea of diffusion, but water being such a universal, unique component for life, it just has its own word. It's special. It gets its own word. So osmosis, and this requires a membrane. So think of like dialysis, for example. You've got a water-based solvent with a solute, and you're able to move things across that membrane, across that kidney membrane. That's osmosis. Whereas diffusion can move from an area to high to low concentration, like in a room. It's not needing to go across a membrane, but it's still moving from high to low. So that's passive transport. Your body relies on that in order to move around solutes and solvents to maintain homeostasis or equilibrium in your body. Active transport is next. Active transport is the movement of substances using energy. So this is different because it requires energy. So it's the movement of molecules from low concentration to areas of high concentration. This is the complete opposite movement because it has to go against the grain from areas of low to an area where there's already plenty there. This takes energy. It's going against the concentration gradient. Okay, so this takes energy. Active transportation is needed, for example, in like cell communication. So when your cells are communicating and sending a signal from one part of the neuron to another, or from one neuron to another, there are channels and pumps at play. And you've got like a sodium potassium pump that's constantly working in your neurons to maintain homeostasis. And these pumps are going against the grain. They're constantly using energy to swap out sodium and potassium ions. Well, there's channels that use diffusion too, but that's just one example of active transport that's constantly taking place in your body, moving those solutes, sodium and potassium ions, in your water-based body environment, the solvent. All right, let's take a moment to practice. Sugar, salt, and alcohol and oxygen are all what kind of substances that are attracted to water molecules and dissolve in water? Are these types of substances hydrophilic, nonpolar, hydrophobic, or insoluble? They're attracted to water and they will dissolve in water. What does that make them? I'll give you 1 minute. Okay, sugar, salt, alcohol, and oxygen, if they are able to dissolve in water and they are attracted to water, you have to remember water is polar. And if it likes water, it's attracted to water, it will be hydrophilic. So your correct answer here is A. If they are attracted to water, then they are hydrophilic because hydro is meaning water and philic means like. So it likes water, it dissolves well in water. Option B, nonpolar, is incorrect because if it's dissolving in water, then they would have to be polar because water is polar. They cannot be nonpolar. They would not mix well with water. So that rules out B. Option C is hydrophobic, meaning it hates water. It's water fearing. It would not dissolve well if it hates water. So C can be ruled out. And option D, insoluble, means that they don't dissolve. But the question says that they do. So this option is also quickly ruled out. Next practice question says distinguish between passive and active transportation. So take a moment to, in your own words, distinguish between passive and active transportation. All right, everybody, here's my breakdown of passive and active transportation. I tried to include all details from this webinar lecture, but I also have just like the key distinction at the very bottom, which is a little bit more straight to the point with like a focused concept, but I'll just go back through each one. So passive transport are molecules that will move without the use of energy. Remember that word passive. You're not investing energy into a situation. You're not using energy to move these solutes across, like a membrane, for example. So molecules will travel down the concentration gradient, meaning it just simply moves from an area of higher concentration into an area of lower concentration. Now, the main form of passive transportation is diffusion, which includes the movements of, all molecules. But if you're wanting to talk about passive transportation for just water, that has a unique name and it's called osmosis. But then you also have active transportation, and that takes place in your body too. Active transportation does require energy because you're going like against the gradient or like up the hill, so to speak. You're starting in an area of low concentration and you're moving it into an area of high concentration. So when you go from low to high, climbing a hill, gosh, you're active when you're hiking and climbing a hill. That takes energy, probably some extra energy. Maybe you need to like eat a quick little Snickers bar for some quick carbs to give you energy in order to do that. So going from low to high requires energy. That's active transportation. But the key distinction here, passive doesn't require energy. It follows the concentration gradient. Whereas active energy or active transport does require energy and it goes against the concentration gradient. Our next question says the property of water that explains its ability to be a universal solvent is which option? Which of these explains its ability to be a universal solvent? Give yourself 1 minute. All right, everybody, water is a universal solvent because of its polarity. Okay, so option A is our correct answer here. So water is a polar molecule, meaning it has a partial positive charge on the hydrogen atom side and a partial negative charge on that oxygen atom side. This polarity allows water molecules to interact and dissolve with other polar substances. So it can bond to other negatively charged things and it can bond to other positive charged things. And so let's go ahead and rule out the other options. So option B and C are incorrect. We know high surface tension and high specific heat are unique properties of water, and that allows for life to exist. But this question is geared towards it being able to dissolve other things. And high surface tension, that's due to cohesion. That's just its ability to stick to itself and things to like be able to stand on top of something. It's not really dissolving a solute. It doesn't apply. Same thing with high specific heat. This is unique for water. Water has a really high specific heat, and that just means that it can retain or it can actually withstand changes to heat or heat loss. It takes a long time to heat up. It takes a long time for it to cool off, but it's not really addressing its ability to dissolve solutes. And then option D is incorrect. The kinetic energy of water as a liquid is similar to other energy levels of a liquid. So this is not truly unique, nor does it allow it to be a universal solvent. Okay, we're wrapping up 3.5, and as we review, these are some of the major takeaways. Solutions are made up of a solvent and a solute. Remember, the solute is the lesser amount of the substance in a solution. A solubility is how well that solute can dissolve in that solvent. And that just depends on if it's hydrophobic, it's water hating. Is it hydrophilic? It's water loving. And that is, you figure out because if it is polar versus non-polar. There are different types of solutions. You can have unsaturated solutions, you can have saturated solutions, and super saturated solutions. And the saturation we can measure using concentration. So how many particles are in that solution? Is it really concentrated? So is it saturated or supersaturated? Or is it not so concentrated and your solution is unsaturated? And there are properties of water that are unique and allow for life to exist. Remember, those properties are hydrogen bonds, cohesion, adhesion, high specific heat, and being a universal solvent. And then finally, we transport molecules all the time in your body to keep you alive, to maintain homeostasis. And transportation of molecules can either be passive or it can be active. And remember, with passive transportation, you can break that down further into diffusion versus osmosis. All right, guys, we are on our last section of our chemistry crash course webinar tonight. This is acids and bases. So if you've hung with me this long, thank you. I know we are definitely past our 8 o'clock time limit, but with this being our first chemistry webinar in a while, I couldn't end it abruptly. We had to get through the whole thing together. So thank you for hanging in there with me. And don't forget, as we wrap things up, to check out everything else we have at Archer Review. As I've said before, this goes fast. I am certainly not giving all the details that I could. And there are more practice problems for you to apply your learning to. And you can find all of those resources at Archer Review. Check out our on-demand videos. Check out our 1,500 free question bank. We have so many awesome resources for you. And don't forget to find time with our tutors. And I can talk more about that at the end, but just in case you decide to hop off a little early before I get to it, I just thought I'd share all that with you one more time. And don't forget to take the survey so that I can help improve all of my lecturing in my webinar tonight for you in the future. Let's wrap it up with acids and bases. A nurse's knowledge of like pH, and pH measures the kind of solution you have. Is your solution acidic? Is it neutral? Is it basic? Understanding acids, bases, as a nurse directly will impact your patient care by guiding the management of this acid-base imbalance in the body. It helps you make choices about like the effectiveness of medications. It helps you understand electrolyte replacements and even like the safe use of like IV fluids. All of these contribute to patient safety and recovery. So let's go ahead and get started with this last section. pH stands for potential of hydrogen or power of hydrogen, and it just measures how acidic or basic a solution is using a scale from 0 to 14. So here is our scale. And I've kind of color-coded things so that you can follow along really easily with what's an acid, what's neutral, what's basic. So on this scale, we've got 0 through 14. In the middle is 7. Okay, so 7 is neutral because it's right in the middle. It's neither acidic, which is less than 7, and it's neither basic, which is greater than 7. So just take a look at some of the common items that we're familiar with and notice like how acidic. Is it neutral, or is it actually kind of basic that they are? I think it's interesting to see the coffee. So black coffee without anything else is slightly acidic compared to, just neutral, pure water. Our stomach acid is crazy acidic, but when I look at this scale, I'm a coffee drinker. I'm sure many of you guys are coffee drinkers, especially as nursing students. Like you need that caffeine to get you through school. But with coffee being slightly acidic, or maybe, you don't want coffee, but you still need caffeine, so you drink maybe some sodas that have caffeine. Sodas like Coca-Cola, Pepsi, that's even more acidic. So no wonder why, like some of us experience heartburn, for example, or acid reflux, because we're continuously putting acidic items into our body. And your body's always trying to get back to homeostasis and offset that. But if you experience any kind of acid reflux, now you kind of know why, because we're ingesting acidic things. How about the other end, where things are basic? Look at like ammonia and bleach. Oftentimes my students will make an observation like, well, gosh, bleach, ammonia, like that's kind of some nasty stuff. How can it be basic? So we have like this preconceived notion that if something is nasty and harmful, it has to be acidic. But wait a second, if we remember equilibrium and homeostasis, anything away from the neutral is going to be harmful. So bleach being super basic is equally just as harmful. It's just for a different reason. Okay, let's move on to distinguish really between acids and bases. Let's get into the details. So acids have a measurement on their pH scale of less than 7. And it's an acid simply because when it's being dissolved in water, there will be hydrogen ions that break off from that molecule. And those hydrogen ions dissolve into the water, making that water more acidic in nature. So some examples of that are hydrochloric acid. This is a stomach acid produced in order to help break down food and drink in your digestive tract. And then other examples on that list were lemon juice and vinegar, for example. And then bases, on the other hand, they have a pH measurement greater than 7, and they're a base because they release a hydroxide ion. So they have an OH that will break off from the molecule that's being dissolved in water. So a classic example of this is sodium hydroxide, NaOH. It's a pretty strong base. That OH part will dissociate or do like a double displacement reaction. The OH breaks off from that NaOH compound, and the OH dissolves in the water, making it more basic in nature. So examples of that are baking soda, bleach, and bicarbonate. Bicarbonate is a pancreatic juice, actually, that helps to neutralize your stomach acid before that acidic chyme that gets digested reaches your small intestine. So we need the acid to break down your food, but that acid is super strong. Back on that scale, what was it, like a 2? I think it was, oh, it's a 1, a 1. So it's really strong stuff. If we didn't try to neutralize that acid and it just continued through your digestive tract, that would not be a very pleasant experience. So you've got bases like bicarbonate that's released from other accessory organs in your body to help neutralize that overall solution that's being passed through. So let's talk about neutralization reactions quick. These are acid-base reactions that typically form water and some sort of salt when mixed together. So when equal parts of an acid and a base are used, the system will become neutral. They kind of like cancel each other out. You'll end up with a pH of 7. So it's, like I said, as if they almost cancel each other out. And notice that it is a double displacement reaction. So when we have hydrochloric acid, strong acid, mixing with a strong base, see how that hydrogen swaps with the part of the other reactant. We have the double displacement flip-flopping parts. And we end up with sodium chloride, which is salt, and water, which is neutral in the end. So acids and bases, when chemically reacting together, will neutralize each other and create a solute, which is the salt, in your solvent, which is the water. I should mention that these neutralization reactions really help to maintain the overall pH of your living body. I mean, any living thing, but like, for example, in the human body, the blood pH is regulated through different buffers that will involve neutralization reactions. So we're just making sure that your blood pH doesn't become too acidic or too basic. These neutralization reactions are constantly at play to maintain the overall pH and homeostasis of your body. So speaking of buffers, buffers are pH stabilizers. So again, they help to get back to homeostasis. They help to resist any kind of changes to pH, and they consist of a weak acid and its conjugate base, or a weak base and its conjugate acid. So when an acid is added, that conjugate base in the buffer reacts with those extra hydrogen ions from that acid, and it will reduce the impact of that pH. But let's say you add a base to your solution. The weak acid in your buffer donates the hydrogen ions to help react with the base to neutralize the base. So your buffer is there to just offer whatever maybe is missing to chemically react with what's highly concentrated. If you're high in acid, it's going to react with that acid. It's going to offer its base. If you're high in the base, then it's going to offer its acid to react with that base to get it back to neutral. So some common buffers that you'll come across as a nurse, like sodium bicarbonate. This is something often administered by nurses to help regulate those blood pH levels, like I said. Phosphate buffer is another buffer you'll come across that operates in the kidneys. Although it's maybe not directly administered as a buffer by nurses, that phosphate's just a crucial component of that IV solution that helps to balance all of those electrolytes in the patient, especially if they have kidney diseases. Okay, our first practice question. Which of the following are true about acidic solutions? Select all that apply. I'll give you 1 minute to select all that apply. That applies for acids. All right, everybody, the following are true about acidic solutions. Acidic solutions have a pH below 7. Remember, 7's neutral. Anything less than that on that scale would indicate acid. Acidic solutions release hydrogen ions when dissolved in water. The fact that it releases a hydrogen ion, being a proton donor, that's what makes that water more acidic over time. C is incorrect. We never talked about litmus paper, so hopefully that was a quick way for you to rule out C, but I'll still tell you, litmus paper is a type of paper you can dip into a solution and it turns a color. And that color indicates to you what kind of solution it is. So if the paper turns blue, that means it's a base. If that paper turns red, then that means it's an acid. So just a fun fact, but we never even talked about litmus paper, so hopefully you could rule that option out. Option D, they are found in lemon juice. Yes, lemon juice is an acidic solution for sure. So option D is certainly correct. Option E, they release hydroxide ions when dissolved in water. This is incorrect because that's the role of a base. A base will release OH or hydroxide ions when in water. And then option F, they feel slippery. Again, didn't talk about that property, but if you want to know, bases tend to feel slippery, while acids don't. Now, to clarify, they're all solutions, which means they're wet, so like they would feel slippery to a degree, but even within different types of solutions, some can feel more slick than others between your fingers. Bases will actually tend to feel pretty slippery, while acids do not. Next question. In a neutralization reaction, an acid reacts with a base to form water and what else? In a neutralization reaction, an acid and a base will react with each other to form water and salt. Option D. Okay, so salt, since it's a double displacement reaction, it makes salt an ionic compound and water for products. Option A, carbon, is incorrect. Carbon is not an element in the reactant at all. And so in a neutralization reaction, it can't be a product. If it's not a part of the reactant, it can't be a part of the product. B, metal, is incorrect. Metals are not produced in a neutralization reaction. Sodium alone is considered a metal, but once it's bonded with chlorine gas, it's no longer a metal. So even though we end up with sodium as that salt product, sodium with the chlorine gas is no longer having the same metal properties. So it's not making a metal in the end. And then glucose, we've got as an option, option C, but since there are no carbon atoms in the reactants, we can't have carbon just appear in the products. This is that law of conservation of matter, remember. Hold on, I'm just checking out the chat for a minute. B for solar. Oh, someone brought to light for me when I was rearranging things and setting this up. Yeah, whoever was in the chat and said, wait a second, I answered salt, but I answered B. You are totally correct. I think I rearranged some things as I was playing around with my subscripts to get it to fit. So if you chose salt, whether it was B on this slide or D on this slide, you are absolutely correct. So way to be observant for me there. Salt is correct. That's the major point there. So good work. All right, guys, our final review. So our pH can be measured on a scale from 0 to 14. Remember, if it's greater than 7, it's going to be basic. If you're right at 7 on that scale, it's neutral. If it is less than 7, then it is considered acidic. So know how to read your pH scales. Acids are going to be proton donors. So you know it's an acid in a solvent because it's releasing a hydrogen ion. Okay, that's that proton donor piece. Bases are proton acceptors. They'll take that hydrogen. It just comes in the form of an OH. So it gives off that OH. The neutralization reactions are when the acid and the base make a salt and water, and these are essential reactions in the body because it helps to neutralize solutions as we're moving things all around to different parts of your body. Some parts of your body can't withstand an acid. Some parts of your body can't withstand a strong base, and so they have to be neutralized before it can move from one to another. But you've got buffers in your body to help offset that. Buffers help to regulate pH in reactions. All right, guys, we did it. We made it through our chemistry webinar in just under 3 hours. If you're still hanging with me, thank you so much. I hope you had a nice review of some chemistry basics. I hope I taught you some cool tips or tricks to help you. But if you need more, and I hope you're wanting more, please check us out at Archer Review. But before you do that, don't forget to scan this QR code. Leave me some feedback. This is my first chemistry webinar with you guys. Now, is this my first chemistry lecture ever? By all means, no. I told you guys I'm a science educator during the day, but I want to really cater this to your guys' needs. You're different than my students I'm teaching. You're pre-nursing students, so leave me some feedback, please. Let me know what we did well. Let me know how I can improve for you for the next time. So my next chemistry webinar will be in December. I also have an anatomy and physiology webinar coming up later this month as well. Shelly, our other science instructor, she takes over the biology webinars and the science reasoning webinars. So we've got so much to offer you guys. Just keep your eyes open for us at Archer Review. Don't forget, we've got rewatch webinars. This is a new addition for you, and I think some people are asking about it in the chat right now. If you missed a webinar, if you want to go back and rewatch this webinar, there's a QR code for you guys right there, okay? But you know what's even better? You know what's even better than just rewatching these webinars? Our on-demand videos. Because with our on-demand videos, you can slow them down, you can speed them up. You don't have to watch the whole thing again. You can go to a specific area that you're like, man, I really need more practice with this. Some people are asking about in the chat, like, help me better understand factors affecting chemical reaction rates. I love that you're wanting more. That'd be a great place to go in our on-demand videos. Go look for that special timestamp about factors influencing chemical reaction rates. And then you don't have to listen to the whole thing. You can just focus on the skills that you're wanting to improve on. And some of you, maybe you want some more questions. We've got a free question bank for you. So scan that QR code, get access to so many more questions. And don't forget, next slide here, tutors. We've got some of the best, you guys. Tammy can help you with English and reading. Shelly, my other science educator with me, she has availability for science tutoring. Check her out. Brandon Kraft is the math guru. He's the math expert. He's been at this for years, you guys. Sign up for some tutoring with these guys. You can get a better rate if you guys sign up as small groups. Then you guys can split that cost for a tutoring session. But I'm telling you, we have so many opportunities for you guys to really cater your needs for what you need in your pre-nursing journey. So we are here for you. Find us, reach out to us, utilize us, and I hope to see you guys in our next upcoming webinars. Someone says, is this webinar science or chemistry? This webinar is both, because science includes chemistry. Chemistry is a science. So this is the chemistry webinar, but we also have other science webinars available. Like I said, the anatomy phys, biology, and scientific reasoning. And I did share the PowerPoint at the start of this chat, but I will go ahead and share the notes with you guys one more time in our chat because some people are asking for them. So here's the link to those notes that I just lectured over with you tonight. So hopefully you guys are able to access those. Let me know if that link is not working for you, but it should. And if you signed up for this Zoom webinar ahead of time, check your emails because that also gets sent in your email as well. So how can you get a replay of this webinar? I'm going to go back to this screen right here. See this rewatch webinar. You scan this QR code, and this will take you to all of our previous webinars, not just tonight. I mean, feel free to replay this one, but you can rewatch any of our previous webinars by accessing this QR code. It'll take you to our playlist, and you can just scroll through which ones you need at the time that you're studying. Okay, just seeing if there's any more questions coming through before we hop off. Leave a QR. All right, guys, if you don't have any other questions, thanks for joining us. And I hope to see you guys at our next webinar. I'll linger around just for a couple more moments for those who have questions. I'm answering you privately right now. So take a look at those if I haven't addressed it. And I hope you guys have a great night. And I hope to catch you in our next webinar.